So welcome back, everybody. And the topic this week is going to be first a recap of diagram rules with applications. And then I'm going to mention, I'm always in doubt whether I should go through the proof or not. There is a detailed derivation in chapter 6 of Shavit and Bartlett, which to many is essentially incomprehensible. The proof which I like is one which is based on time-dependent perturbation theory. But if we want to cover that as well, we would not have time for copper cluster theory. So I've decided to kind of strike a compromise where I cite what the linked diagram theorem is without going in detail through the proof. And then I'm going to discuss a little bit about what these linked and unlinked diagrams are. In the lecture notes from last week, there are elements which I want to repeat. And we are going to spend some time today on this topic because that also links with the second midterm, which you have available now. I just put it up this morning. And it's essentially the same as we had last year. And this is a midterm where we look at methods like full configuration interaction theory, Hartree-Fock. Actually, you will notice that you are already in a Hartree-Fock basis. So in one of the exercises, you're asked to set up the Hartree-Fock equation and solve the problem, but you don't need to do anything except setting up the equations because the basis you have is already a Hartree-Fock basis. And that's something which we want you to see from the equations. So you would need to set up the equations, but when you've set up the Hartree-Fock equations, you will see that, hey, there is nothing to do here. Okay, so these are the kind of things we want you to view. So it's a kind of reminder of the mean field method. And then we are going to calculate the terms in which we can get for the coefficients from the exact diagonalization. And the case you're going to look at is a 6x6 matrix. And we are going to get these coefficients, which you get from the diagonalization, from many-body perturbation theory. And you're going to make a comparison between many-body perturbation theory to a given order, and you will see that there are only some limited numbers of diagrams which contribute. So I actually wanted to use this lecture here to, to capture many birds with a stone by looking at both linked and linked diagrams and a recap of diagram rules, okay? And then tomorrow, and if we get time, we will start with copper cluster theory, which is a widely used many-body method in atomic, molecular, nuclear physics, condensed matter physics. And there are many approximations to that method, and we are going to discuss some of the most common ones, which often leads to what's called the golden standard in many-body physics as an approximation to the problem. And for those of you who will deal with these type of methods, copper cluster theory is a kind of a basic method in many-body physics. It strikes a compromise between the number of floating point operations you want to deal with and the accuracy which you can get. So if we now look at the topic for tomorrow, we will discuss a little bit more at length the second midterm, and we're also going to continue the discussion of copper cluster theory, which will keep us busy for the last 2 weeks of the semester. So the last lecture is actually Friday, the 28th of November. And the relevant chapters, both on linked diagrams, is chapter 6. And for copper cluster theory, which we'll begin with, the most relevant is actually chapter 9. And then we will move over to chapter 10 as well of that textbook when we look at the general copper cluster equations. For the midterm, in case you would like to add that to the oral examination, I'm going to give you programs for the copper cluster method. And that program implements essentially what chapter 9 does, apply to that simpler Hamiltonian, which we have in the second midterm. And the second midterm is a classic Hamiltonian, which is the so-called pairing Hamiltonian, which was suggested by Bardeen, Cooper, and Schrieffer to explain superfluid conductivity. And to them, it actually gave the Nobel Prize in physics. Bardeen actually got the Nobel Prize twice for his work on semiconductor physics. Okay, so I just wanted to, if we just go out of that one and then look back at the slides from last week. So just as a mention here, I didn't make a video for Friday, but the material for Friday is essentially covered by the slides which you see here. And for those of you online, I'm going now just to change so that we can share that screen here. So I'm just going to change a little bit, and then we switch over to the whiteboard quickly. So in those slides, what we have is a summary of the diagram rules. So let me just bring them back here again. So the standard rules which we are going to play around with again and again now is first that you have the vertices. So each interaction vertex contributes a factor if you have a two-body interaction. With two incoming, if you're whole, then you have whole lines. They don't need to be whole lines. You can stay in the particle formalism, and two outgoing lines. And they are summed over all the internal indices. Then each internal line corresponds to a contraction and implies a Kronecker delta enforcing index matching. And whether that index is a particle, unoccupied, or whole, which is occupied in the state. And then there's an energy associated with that orbital. And that contributes to the so-called energy denominator. Then we have this signs, and there is a sketch of a proof in the slides from last week. And that includes a global factor, which comes from the reordering of fermion operators, which are needed to realize the contractions. So the equivalently, you can actually look at the number, when you look at the diagram, at the number of fermionic line exchanges. Then in between each vertex, there is a energy denominator, which goes like the energy of the first non-interacting ground state minus the energy of the intermediate states. And I'm going to remind you of some of these practicalities. Then, so if you look at the example which we have here, this second order diagram, which is a two-particle, two-hole excitation, then if you look at it diagrammatically, you would have to draw a vertex for the states where you go from IJ to AB, so that's the two-particle, two-hole excitation, and then the other vertex, so when we look at the diagram now, actually de-excites from a two-particle state down to a two-hole state. So essentially what this diagram represents is a two-particle excitation, which is two-particle, two-hole excitation, which then represents an intermediate state, and then the system gets de-excited by new interactions and goes back to the ground state. And you have the internal lines when you do the contractions, which contract with these different lines. And then the denominator is the energy difference of the intermediate two-particle, two-hole line. And then you have in that case, you have two whole lines and two loops, and that gives a factor of +2. So the symmetry factor is the one which gives a factor of 1 divided by 2, and that is due to the symmetry of the interactions. And there's a sketch of the proof down in the slides here. And we are going to now just look back at some of the diagrams and try to practice. And we're also going to introduce something which is relevant for the second midterm, which is the wave operator. And from the wave operator, we are going to look at linked and unlinked diagrams and what they actually mean. And that leads also to a theorem, which is called the link diagram theorem. So here you will also find the final recipe. And these rules simply follow from applying Wick's theorem. There's a conceptual proof here. I'm not going to go through that one in the lecture today, but I wanted to state the so-called link diagram theorem. So we are summing over all the intermediate states, really. And the final contribution is a contribution which only includes so-called link diagrams. This is important also when we look at copper cluster theory. So I'm not going to make a proof here. There's a sketch of the proof in the lecture notes from last week. And you will also find elements of that, or there's a whole chapter in Shavit and Bartlett in chapter 6, where they actually prove the link diagram theorem. But this is something which we are just going to use. I don't want to spend time on proving it, so I leave it to you guys just to go through that chapter and convince yourself about the statements there. So what I want to do now is actually go back to the whiteboard and be a little bit more practical and try to link the things you will see with what you will get, what you will find in the second midterm. Because in the second midterm, we're actually going to calculate contributions to perturbation theory to a given order. And we are going to compare these contributions with exact diagonalization. And that hopefully gives you a little bit deeper insight about what many-body perturbation theory is doing. So it's a recipe where you order by order can actually get an approximation to the exact coefficients you get from diagonalization. Okay, so let's now jump into the whiteboard and do that. So one of the things which we looked at last time was an example of a perturbation theory contribution to second order. And when we looked at that, we had two possibilities. So let's just quickly remind ourselves about that. And this is Rayleigh-Schrödinger perturbation theory, but I'm just going to call this for many-body perturbation theory to second order. And what we had were contributions of the following type. So we had a diagram, which we call for a one particle, one hole excitation. So we had A and I here, and then we had the closed loop with K and J here. So that was one of the contributions we found. And this is when you now look at the intermediate state, this is what we would call a one particle, one hole excitation. So I'm coming back to these things again. So there will be some elements of repetition, and this is done on purpose because I want to link that with the second midterm, because there are some questions there which will link with the way we look at perturbation theory, and in particular, the approximations to the wave function. And then we had another contribution, which was given by this diagram here. So we have labeled all the lines. And if we're going to use the diagram rules, it means that we have to sum over all the intermediate states. So this diagram, which you see here, the second one is a intermediate state with a two particle, two hole excitation. If we now write down the contributions to the analytical expression for the energy, this diagram here has a sum over A, I, J, and K. There is a vertex. Normally, when I set up the vertices, I begin at the top. So I have an outgoing hole line, which is an I here. I have an outgoing hole line K. I'm skipping the anti-symmetrized subscript. I'm assuming now that all these integrals which you see are given by the direct term and the exchange term. So I'm going to skip the AS subscript, which we have normally used, just for simplicity. And then we have a incoming particle state and an incoming hole state here. And then we have a outgoing particle state I, an outgoing hole state J, we have a V, and then finally we have an I and J coming in here. And there's an energy denominator, which is simply the difference between the number of hole lines and the number of particle lines here. So this goes like epsilon I minus epsilon A. The number of hole lines is equal to 3 in this case, and the number of loops is equal to 3. So that means that we get minus 1 to the power of 6. And the number of equivalent pairs, in this particular case, number of equivalent pairs, which gives a symmetry factor, is equal to 0. So that means that we get 1/2 to the power of 0, which is just 1. Now, in the second diagram, on the other hand, we have two equivalent pairs. So I'm just going to set up the expression again. We are getting a factor 1 divided by 4. So we have two particle lines which start at the same interaction and end at the same interaction. We are summing freely over the intermediate states. So that's one of the diagram rules which you saw. And then we have the final state, Ij, and we have AB. So we create an intermediate two-particle, two-hole excitation by removing two states in the states I and J below the Fermi level, and we are promoting them to the states A and B above the Fermi level. And in this case, we have epsilon I plus epsilon J minus epsilon A minus epsilon B. And here we have a number of hole lines equal to 2, number of loops is equal to 2 here, and the number of equivalent pairs is equal to 2. And that leads to a factor 1/2 to the power of 2, which is the one we have there. So when somebody gives you a diagram, you have a very compact way of expressing a physical contribution or contribution to many-body perturbation theory. We will see much of the same in copper cluster theory, and the copper cluster theory equations, which we are going to develop, we can do that algebraically. But when you get acquainted with diagrams, you can derive the same equations by combining different diagrams. And that's the power of these methods, because you can actually look at the diagrammatic expressions and then see whether you have missed something or not. And then from the diagrams, you can recover the analytical expressions. So we're going to use that kind of reasoning, because if you look at what we have done here is to assume that we start with the ground state, we perform a two-particle, two-hole excitation, and then the system lives in an intermediate state here, and then gets de-excited, and then you're back to the ground state again. So that's the way you can give a kind of pseudo-physical interpretation of this process. So I say it's pseudo-physical because you actually have to sum these terms to infinite order. Okay, so one thing which we have done now, when we look at the contribution to the energy to second order, and this was this term here, this was given by us setting up phi 0, the ground state, and then we had the interaction h of I. Then we have this denominator q divided by E0 of h of I. So this is an I here, and phi 0. And now I'm just going to replace this one with another operator. So these are operators all. And I'm just going to call this for R, which links with the resolvent, which we defined earlier. So I can actually rewrite this as a phi 0, and then I have my h of I multiplied with this operator, multiplied with h of I, and phi 0. Now I can actually rewrite this now, since we have the Hamiltonian here, the interaction piece to first order. The whole contribution is to second order, but I can actually rewrite this now in terms of phi 0, and then I have the Hamiltonian acting on a state, and I'm going to call this state for phi 0 to first order. So this state here is actually now given by the following. So I have a wave function. So my wave function, the approximation I'm making to first order, is given by this operator R, multiplied with a Hamiltonian, and acting on phi 0. Now, that means that if we look at the equations we have, we would have the following. So this equation here, if we now go back to the terms which we put up here, these terms, the full ones, what we have then is something like this. And this follows very much what we are doing physically, because you could now think of you having the system like this. So you create a two-particle, two-hole excitation with an energy denominator. So I'm going to write this with a bar here, because it contains not only the interaction, but also an energy denominator. So I'm acting with this R on this h of I times phi 0. And in our case, this is now given by these intermediate states of m larger than 0. I have this phi of m multiplied with the integral phi of m h of I phi 0, and divided by the denominator So this term which you see here, this one, is actually the same as this operator R. Okay. So I'm just rewriting terms. And the reason why I'm doing this is that when you now are going to, in the second midterm, when you are going to make comparisons with the full configuration interaction wave function, these terms which you see here are then going to produce the same terms, but approximated to first order in the interaction. So let's try to look at the mathematical expressions which you have. So what we end up with for this specific case to second order is that this first order in the interaction. So that's why I put psi 1. So the energy comes to second order because I multiply with the Hamiltonian again. This is given by 1 divided by 4. There is a sum over AB, ij. And this is the guy which now has been produced as an intermediate state. And this is multiplied with phi ij of AB divided by epsilon I plus epsilon j minus epsilon A minus epsilon B. And in addition, what we have is a new term, which you will see to your great pleasure in project number 2 here in the midterm, that these actually are 0 with the type of Hamiltonian which you have. So there are some simplifications which take place. But this is actually your wave function to first order in the interaction, like that. So what we are doing physically now, if you think of this term here, so we have created now a two-particle, two-hole excitation, and this is now the coefficient in front of it. So if we go back a little bit here and look at the FCI calculations which we did, so in FCI, what we had then is a wave function, a psi 0, which is then given by an operator, which we call the correlation operator, 1 plus this C hat acting on phi 0. And the C hat here was actually this sum over particle hole excitations. So we have a CIA, and then we have the phi IA, we have plus of AB, IJ, CIJ, AB, IJ, AB, and this just goes on. So when you diagonalize 4 particles here, there will also be a 4-particle 4-hole excitation here. Now, when you look at what we have here, you will now see that many-body perturbation theory, when we now look at the wave function, many-body perturbation theory gives us this term, which should correspond to this one. And it gives us also this term here, which then should correspond to this guy, but then to first order in the interaction, if we do the energy to second order, okay? So when you are going to diagonalize now, you will have a 6x6 matrix. If you take away 4-particle 4-hole excitations, which is a simplification of the problem, you have a 5x5 matrix. And that means that you will have, since you have an overlap with the ground state ansatz itself, you will have 4 such coefficients from this term here, which you then can compare with what you get from many-body perturbation theory directly. Because the interaction which you're going to have in the midterm is just given by a constant G. These energies are easily evaluated. And then you can pick the 4 different 2-particle 2-hole states and make a direct comparison with what exact diagonalization gives you. And what you will see, and this is where we want to trigger your physics intuition, is that if the interaction is very weak, then perturbation theory is going to do a pretty good job. If the interaction gets strong, you will then start seeing deviation from exact diagonalization and what perturbation theory gives you. And it's actually this kind of balance we want to see. And in this simple model, which you have in this second midterm, you can actually play around and get this kind of intuitions. Okay, so let's look at this diagrammatically, because we can also present this diagrammatically. And what you would do then, since we now have created an intermediate state here, which is a two-particle, two-hole state, but then we have this interaction element, the way you can think of this is now as follows. So, and this is something which we are going to use in particular when we go to copper cluster theory. So if you look at this interaction vertex, which we have said creates a two-particle, two-hole excitation, this is just given now by a term which goes like A, B, I, J. So we have A, B, and V, I, J. But then we can now rewrite that one where we also add the energy denominator. So this term here is without the energy denominator. And then we would simply rewrite this in terms of a coefficient, but where we now have a solid line here. Then we have A, B, I, J. And this is now going to represent A, B, V, I, J divided by epsilon I plus epsilon J minus epsilon A minus epsilon B. So when you look at this kind of different notation here, it's a way to indicate that you have actually calculated something which is not only this one, but it includes something more. So later you will see that this can be opened up and it will contain many, many more contributions. So now it's a contribution at first order to the wave operator, but there is nothing which hinders us to rewrite this one, use this compact notation to indicate that this contains more than just the interaction to first order. So it's often used as a compact way of indicating all the physical processes which took place before a given time t. So then finally what we get is the contraction. So we can contract it either with this one, because we have created a two-particle, two-hole excitation. So this is actually going to represent the whole thing here with phi ij ab, so which we had actually here. So our contribution to the coefficient is going to be this one. So this means that when we look at these contributions, we could now think of just writing the diagram by, we can perform contractions either with this one. So this is already closed. So we can have A and B, I and J, and then we have A and I and J here. And then if we look at this specific contribution, then we have I, J, A, and B. We see immediately that since this guy here is a two-particle, two-hole term, this is a one-particle, one-hole term. This is a two-particle, two-hole term. This process here represents a de-excitation back to the ground state. Here, I could only link this one with that one, and that will leave these two uncontracted. And I know that if I take the contraction between these two guys, that should give me zero because they're different. So the only diagram which I can link this one is actually with that one. So that gives us then, if we now look at this kind of new notation which we have, if this was to be only to second order in the interaction, we would then have a dotted line. But now we could indicate that this one actually has more than just second order in the interaction. And this is something which we are going to look at now. So now we looked at the wave operator to first order. So let's look at the wave operator to second order. And this is going to bring in a slight modification. So here previously, we had the wave operator to first order in interaction. But we can continue like this and go to second order. So let's just write down the contribution to second order in the Hamiltonian. So this is something which we can then write as a sum. And now I'm setting up the expressions which we get when we look at Rayleigh-Schrödinger perturbation theory. So in that particular case, what we had is an intermediate state, phi of m. There's a new guy, phi of m here. We have the Hamiltonian. And then we have the intermediate state, n. And they are all larger than 0. We have assumed a degenerate and non-degenerate ground state and only one. And then I have a h of I, the interaction again, and then the ground state. And this is divided by epsilon 0 minus epsilon m multiplied with epsilon 0 minus epsilon n. And then there is another term. And this other term runs like this. So there is a summation over m larger than 0. I have a phi of m, and then phi of m, the interaction, and then phi 0. And this is divided by epsilon 0 minus epsilon n squared. But it's also multiplied with a new term. And this is a term which then gives what we call an unlinked diagram. So to get the total energy, to get delta E0 to third order, then we simply multiply with phi 0 and h of I on the left. And then we get the energy. So let's try to take a look at these different terms here. So what we're going to do now is just to look at this term, and let's see what kind of contributions we can get to the wave operator, because this is going to be an operator. Because remember now that these guys are integrals, integral. These are just numbers, and the operator comes from this part. So you could have a two-particle, two-hole intermediate state. So if phi of m is a state of the type phi ij ab, then this is going to be a two-body operator. So that means that we will get an A dagger, AB, AJ, and AI. That means that since this is a two-body operator now, we need also to take into account the fact that we need to have it properly antisymmetrized. So what we would need then, if this takes this form, we will need a factor 1/4, because then this will be an operator. So this is an operator. So you have all constants here, but then you get this intermediate state, which is defined in terms of these creation and annihilation operators, and this is multiplied with phi 0, obviously. Okay. So let's now look at a typical contribution which we could get. And let's do this diagrammatically. So we can rewrite this in a more compact form. So let's just look at the first term here. Because the second term is going to give us what is called an unlinked diagram. So let's look at the typical example. So if we compactify this in terms of that operator R, this is going to be given by the operator R times h of I, and then I have the operator R, and then I have h of I, not that one. And this is then multiplied with phi 0. And then we have the other term, which is simply given by, if you now look back here, this contains now the wave interaction to first order. So it has this operator. So it contains now an R, but I'm going to rewrite it a little bit because it's going to have R here, but it will have the energy denominator. So it's going to have this intermediate state, phi of m, and then I have h of I, and then I have phi 0. So I'm just going to write it like this, and now I'm going to focus on this term here. And this one is then epsilon 0 minus epsilon n squared and multiplied with phi 0 and h of I phi 0. So let's now focus on this term only. So one typical contribution which we could have could look like this. So we could now make a two-particle, two-hole excitation. And we could have the two-hole states which enter the diagram like that. And then I have an interaction piece. So I have particle states, two particles leaving. But what we could have then is that we create an intermediate particle state, A and B. And then we get a new interaction and we create a new two-particle state. So the end product is a two-particle, two-hole excitation. Now, this is going to be an operator. And in this specific case, we actually have a term which is going to be proportional since we have the state, a new final state. We are going to have a summation which will contain a factor 1 divided by 4. I'm going to have A, B, C, D, I, and J. And then I have the interaction piece itself. I have C, D, V, and A, B. And then I have my A, B, V, I, J. And this is divided by epsilon I plus epsilon J minus epsilon A minus epsilon B, multiplied with a new denominator, which is epsilon I plus epsilon J minus epsilon C minus epsilon D, and then multiplied with the final state, which is leaving IJ and CD. So what we have now is two energy denominators because we have two of these operators are here, and each one of them gives rise to this one plus that one. I have the final states, two particle states C and D, and I have my A and B's, and then I have the final state, which I'm getting here, which needs to be contracted when I calculate the energy, because the energy would then imply that I'm having phi 0 with the interaction, and then this is multiplied with this psi 2, the wave operator to second order. So this, when we contract that one with the final term, this term here, then I need actually to set up a final interaction here, which is then going to contract with these ones. So the final energy is going to look like this when I draw the diagram. When I then contract it with the two-particle, two-hole D excitation, I'm going to have a whole state like this. And then I have my, sorry, not like that. I want to have it like this. So this is my I and J. And then I have the two particle states, A and B. And then I have my C and D here. That's the final contribution to the energy for one possible combination. So I can have other types of operators. I could actually have an operator which looks like this, alternatively. So I'm just drawing examples now, and I'm not going to set up all the expressions, but I just wanted to draw examples. And then if you then want to compare third order calculations with the diagonalization and see what kind of contributions you get, you could have diagrams like this one. So where these could be whole lines. This is a whole line. So I would have an I here. I have an A and a B. This is a C. And then I have a J and a K here. So that could be an example of another type of wave operator. And this needs also to be contracted with a term. So both of these terms can only contract because this is also two-particle, two-hole excitation, but now to second order in the interaction when you look at the wave operator. So you can think of you now perturbing the system, and you create an intermediate two-particle, two-hole excitation, but where this now contains higher order terms. It's not to first order, it's just to second order. And you see when you go to third order, fourth order, etc., you get more and more complicated contributions. And this needs to be contracted with a term like this one. So this one led to that diagram here, but when I contracted with this one, this is going to give me a diagram which is a little bit different, which is going to look like, but it's at the end, it's going to look like this. So it's going to have this term, and then it will have these lines here, and then it's going to be whole lines. And then I'm going to have a, sorry, not that one, but I wanted this one. So these are going to be particle lines. I have a state I have a B, and I have an A, and then I have my whole lines J, and I have the whole lines K, but then I have a particle line C here. This also produces a two-particle, two-hole excitation. Alternatively, I will also get a contribution which looks like this. So this is also an intermediate state which I can produce. And then I have a C here, state C, a state B, a state A, and a state I, and a state J here. So this diagram produces what we would call an intermediate two-particle, two-hole excitation here, because I have two particles and two holes. But then I cannot contract this one with that one, because that would leave out two uncontracted lines, and that will give us 0. So the only one which can match this one would be something which looks like this. And this is, in our case, what we call the Hartree-Fock diagram. So if I do that, then I could contract this line with that one, and this whole line with that one. And that would result in a final diagram which looks like this. So I would get a diagram like that, where I now have the two-particle, two-hole, or the final line here, but then I have something like this. So in here, I have created a two-particle, two-hole excitation, but here I have only a one-particle, one-hole excitation. So let's just set up this as a final example of a diagram which we can produce. So it means here that what we have, if we now put labels, so we would have an A here, we have a J, sorry, an I, a J here, and then we have a K here, and an L here. Now, this case has 3 loops, and loops equal to 3. So the loops are this one, and that one. And then we have 1, 2, 3, 4 whole lines. So that gives us n equal holes equal to 4. So that is going to give us a factor of -1. So we're going to have -1 to the power of 7, which is -1. In this case, we have no equivalent lines which start at the, actually we have an equivalent line which starts here and here, a pair, and then ends at this interaction vertex and that interaction vertex. So the number of equivalent lines here, or equivalent pairs, is equal to 1. So that gives us a factor of 1/2. So this diagram is going to be given by -1/2, and then I'm going to have a sum over the particle states. So there's a particle state B here, which is AB, and then I have I, J, K, L. And I'm going to set up the interaction elements. And so I'm going to have a whole state I and a whole state L, a particle state A coming in, and a whole state L coming in. And then I'm going to have in the next interaction, I have a J and a K, I have a V, and then I have a J, no, sorry, a state I and a B. And finally, I have a state A and a state B leaving, a V, and then I have a J and K entry. So I create a two-particle, two-hole excitation. One of them gets de-excited, and I'm left with a one particle, one hole excitation, which then gets de-excited again, and then I'm back to the ground state of the system. The energy denominators, when I now just look at the hole lines in between the vertices, these two lines which we can draw here, then what I get is an epsilon j plus an epsilon k minus an epsilon a minus an epsilon b. And this is multiplied with the next one, which is simply an epsilon I minus an epsilon A. So in this way, we could then extract the contribution to total energy. Now, the wave operator in this specific case is actually going to be given by these terms here. So the coefficient, if we want to make a comparison with a different contribution, this is actually what we should get. Okay. So what we have looked at now are contributions to third order in the interaction for the energy, but which stem from the second order term in the so-called wave operator. So in this case in particular, what we looked at was actually this term here, this one, but we did not look at this term. So let's take a closer look at that one, because this is going to give rise to what we are going to call unlinked diagrams. So the unlinked diagrams are diagrams which it's pretty intuitive to understand what they actually mean, but let's take a closer look at them. Let me just find my cheat sheet here with the diagrams. So if we now look at in more detail at this term here, this is going to create a one particle, one hole, or two particle, two hole excitation. On the other hand, this term here is just an excitation by itself. So let's look at how this translates into the particle formalism first. So let's look at the unlinked diagram. In a particle formalism. So I'm just going to write them down in a way which is hopefully easier to understand. So what we have is a term here, which is this one, and that creates an intermediate state, but it has an energy denominator squared. But let's now look at what this could look like when we are now setting up the diagram. So I could have something like this. So this is in the particle formalism, and then we can actually turn this into whole lines. So I'm indicating this as a state below the Fermi level, K and L, like this. And then it creates, and we mark this in the particle formalism as a particle state. So this is a state A and a state B. So, and it has an energy denominator squared. And then if we now look at the other diagram, you could now think of this term, which goes like phi 0. And then we have the interaction and phi 0. So a typical term here could be something which looks like this. So we would have a state I and J coming in, and we would have a state I and J coming out. Sorry, this is not supposed to be an I. And this is going to be a J. So this could be a typical contribution to the wave operator. Then we are going to multiply from the left of the contribution to the wave operator. So if we take the wave operator, which we have here, and then we multiply with phi 0 and h of I against this one, then it's obviously this state which has to be connected with the interaction. If we also look at what we have here, if we look at this intermediate state, which you have here, this is a two-particle, two-hole. So we have two states above the Fermi level and two below. We are just writing this in its full glory in the particle formalism with respect to the true vacuum. But if we now single out these lines here, you see that this one is okay because it's a two-particle, two-hole state. And then if I look at this one, this is also okay because it's a two-particle, two-hole state. So these are intermediate states which are different from the ground state. And keep in mind that in the definition of many-body perturbation theory, the intermediate states are not equal to the states which you have defined in the model space. In our case, it's only phi 0. Then this will be multiplied with the final piece, which then could be a state K and L. So what we would get then, if we look at this in the particle formalism, we could get a diagram which looks like this. So I have I and J here. And then I could now get the corresponding hole states. So I have a particle states here. So I have my A and B, I have my K and L, and then I have my K and L coming out here. Now, if I want to write this in the particle hole formalism, if I do that, then I would have to bend this one so it meets that one because I'm summing over all the intermediate states. I would have to bend this one, and I will do the same here. So in the particle hole formalism, this guy looks like, so we just write pH. So there will be a term like this one. And then we would have a term like this one. So they are multiplied with each other. So with that, and then we have this one, and we have an interaction here, an interaction here. So that's the diagram in the particle hole formalism. So it has labels I and J, it has labels K and L, and then there are particle states A and B here. So let me just blow it up a little bit. So let's just move to the next page. So what we have is something which looks like this. So let's put label IJ, KL, and A and B. Now, we cannot have a diagram like this. So if I look at what I put up here as an intermediate states with I and J, so I cannot have something like this. So we're just going to put a cross over this one. And the reason for that is simply that the intermediate state here is just a two-hole state or state below the Fermi level, which then belongs to the reference vacuum state. So the intermediate states here, so let's just state that one more clearly. So the intermediate states here, intermediate states have to belong to the excluded space, have to belong to Q, this operator which we then defined as the outer product between these two states here. And if we now go back to the particle-particle formalism, it's actually a little bit easier to see, because if I lift this guy here up above this line, then you will see that there will be no states outside the model space or the P space. So the intermediate states have to belong to this state. There's another problem which you will see here. And the problem which you will face, since we are summing freely here, it means that some of the states here, K and L, could be equal to I and J as intermediate states. So these unlinked diagrams can actually give us diagrams which violate the Pauli principle. Now, this diagram is actually cancelled by another type of diagram. So it is actually cancelled by a diagram which looks like as follows. So this, if you can have a state case here, so let's just set it up. Let me put up the whole lines like this. So this is an unlinked diagram. But then there is a linked diagram. And now I need to set this up correctly here so I don't make a fool of myself, because I always have to, yeah, there is a similar diagram which is linked. We are going to set that one up, which looks like this. I'm going to put labels here. So I have A. And when I'm summing freely, I can actually have two whole states which are the same. I can have a whole state K here and a whole state K there. So that is fine because they are both the vertices. But you see now that this diagram here, due to this one and that one, this violates the Pauli principle. When we break it down in terms of single particle states. And what I could have now is a diagram which is similar, and where I have the states L here, I have a state K here. This would also be a Pauli violating diagram. And then I have a K here, and also I have an B here, and then an L here. So this diagram is linked, and you can show, so we're not going into depth into this one. This is also discussed in chapter 5 in Hjorth and Bartlett. This diagram is unlinked, but you can actually show that these cancel each other. So some of the linked diagrams, which violate the Pauli principle, will cancel unlinked diagrams, which also violate the Pauli principle. What you can show in general is that at the end, when you sum freely over all intermediate states and you violate the Pauli principle, you can show that at the end, the only diagrams which are left in your calculations are the so-called linked diagrams. And that is the linked diagram theorem. Now, these diagrams here in many-body perturbation theory, and these appear in Rayleigh-Schrödinger perturbation theory. If you do Bruyère-Wigner perturbation theory, you will not have that. Now, these diagrams have an unphysical dependence on the number of particles, and they should not be included in your theory. So the linked diagram theorem, which I also have in the slides from last week, is a theorem which simply states that the only diagrams which remain are the diagrams which are linked, and you need to sum freely over all single particle states, so there will be Pauli violating terms, but they will take care and cancel away the unlinked diagrams. So when you set up your expansion, then in your expansion, you will actually have terms like this and terms like that. But then those terms which you get, which give rise to unlinked diagrams like this one, they will cancel terms which are linked and which violate the Pauli principle. That's one type of cancellation. So we are not going more in depth into it, just simply we are going to use the linked diagram theorem. And if you want to look at the proofs of it, you can look up in chapter 6 of Hjorth and Bartlett. So we are going to take a more practical stand here and simply just leave out the proof of it. But one thing I wanted to show you is how you can show that unlinked diagrams have an unphysical behavior. And to do that, this is actually a little bit interesting, because these diagrams, since they are being cancelled, they would then, they should not contribute to the energy. So unlinked diagrams, they have an unphysical property, unlinked diagrams in many-body perturbation theory, diagrams in MBPT and Rayleigh-Schrödinger perturbation theory. They have a dependence on the number of particles, which does not lead to a size-extensive energy. Not what we call are not size-extensive. Extensive contributions to the energy. So we are making an assumption with size extensive. It means that we are assuming that the energy is proportional with the number of particles. So one way to see that is to look at the electron gas. So we can use the electron gas, which we discussed earlier, as an example. So in that case, we had a interaction which depended on the wave numbers. So we have a Ki, we have a V, and we have a Km and a Kn. And this was when we did the analysis for the electron gas. It was given by a Kronecker delta, which conserves momentum, plus a Kj. And then we had a Km plus a Kn. So this is a Kronecker delta. There was a volume element times 1 over V. And then we had an integral. And we are now going to make a simple assumption that this integral is finite and just gives a constant. So we are going to assume that we can calculate the integral and it doesn't diverge. So it has an integral where we integrate over the relative distances. And then we have something like this of K of I minus Kj, the relative momentum, multiplied with R12. Now, this is an integral which we then can evaluate. And when we did that, we found that that term, so this term, let's just wait a little bit so people can write it down. So this specific term is actually proportional to 1 over the volume. So I'm taking away the Kronecker delta, and I'm assuming that the integral can be evaluated. When I then looked at the total energy, which is given by this diagram to first order, so we would have a Ki and a Kj here. When I did that, this was given by 1 over 2. I summed over these wave numbers for all the states below the Fermi level of Kf. And then I simply sum over Ki, Kj, these integrals, which we have assumed are given by a volume-dependent term. And that we use the same trick which we had before. We have K, the summation over K now, which goes over to a volume element divided by 2 pi cubed, and then an integral over K. And then we know that this integral is actually given by the number of particles. So this integral, when we now move over to an integration from 0 to Kf, because these K values go up to the Fermi level of V of 2 pi cubed, and we shift to spherical coordinates over 2 pi over dk cubed, dk vector, where this is equal to the number of particles. And then we know that the density is defined as the number of particles divided by volume. So what we said is that these integrals are simply proportional to 1 over the volume. That means that when we are looking at these terms here, we have twice a summation over the K values. So we should then get n squared divided by volume. So it means that this rough estimates simply tells us now that this term, if we now look at it, so this delta E 0, 1, this is going to be equal to 1/2. And then I have a V divided by 2 pi cubed. I have an integral from 0 to Kf, and then dki. I'm just putting this in a sloppy way because I have the other angles as well, which I'm just leaving out here. And then I have 0 to up to kf, and then a dkj. And this is multiplied with 1 over v. And then there's an integral over dr12 or vr12 times some constants. And then we are just simply assuming that this is a constant. So this is going to be proportional with the number of particles squared divided by v, which is the same as n times density. Now, the number of particles for the electron gas goes to infinity. However, when we look at the energy per particle over n, this is a constant, or it's just given by the density. It's actually proportional to the density. So we say that this quantity to first order is size extensive. When we now look at the energy per particle, because that's the quantity which is finite. And this depends simply on the density. Now, if I look at the second order term, so I'm just going to give you the answer. If I take the delta E 0, so I will just give you the answer here, which is given by this term for the electron gas. This is the only term which contributes to second order. So I have an A and B and I and J. So I'm just going to put up the term here. Now this term is going to be proportional again to n squared divided by v, and that is going to be given by n times rho. So that means that if I then take again delta E divided by the number of particles, this will be proportional with the density. So we say again that to second order, this term is size extensive. If I then go to third order, I will have terms like this one. This is just one of the many contributions. This term will also be, when we divide by the number of particles, it's going to be size extensive. It depends on just n divided by the volume. But if I take this term here, which is the unlinked diagram, which actually gets cancelled. So we don't retain that when we perform the summation over all different terms. So this term here is a term which will actually be proportional to, so this is now proportional with n squared, sorry, n times rho. And this term here is also proportional with n times rho. So what I'm getting then is a term which will go like n times rho squared. And that has an unphysical dependence of the number of particles, because when I divide by the number of particles, so the density is a constant. And if I divide by the number of particles, this is still something which depends on n times rho squared. So because what I want to have is something which simply depends on the density only, which is a constant when I divide away the number of particles. So the behavior I want to have is something which goes like n times rho. The density is a constant, and that means that this is an extensive quantity. It just depends on the number of particles. When I divide by the number of particles, I obviously just get a constant, which is a density. However, when I take the unlinked diagrams, this has a non-extensive dependence on the number of particles, which goes like n squared times a constant. So the constant is okay, but the n squared term is not okay. So the unlinked diagrams do actually have an unphysical size, or they are not size extensive. We want a theory where the energy is a size extensive quantity. Intensive quantities are quantities which pervade the whole system, like temperature or pressure. So every particle feels the same temperature and the same pressure, but the energy is a typical additive term, which then depends on the number of particles interacting. So that's a basic assumption about the energy of a physical system. So this was a very quick and dirty, quick demonstration of the unphysical properties of these kind of diagrams. So to make things a long story short, what we have is a type of contribution from many-body perturbation theory, Rayleigh-Schrödinger, where you only sum up all the link diagrams, but you do sum up freely, so there may be diagrams which violate the Pauli principle. But they will then cancel the unlinked diagrams. And this is the unlinked diagram theory. So one of the prices we pay when we use Rayleigh-Schrödinger perturbation theory is that we get unlinked diagrams order by order. Now, we will get the same when we deal with copper cluster theory, and we are coming back to that a little bit later. So what I want to do now is to switch over to copper cluster theory, and I'm going to show you how we can write the wave function in a very general term using what's called the exponential ansatz, and why this is a valid way to represent the wave function. And this is a very important aspect behind copper cluster theory. So this is our last many-body method. So we have covered full configuration interaction theory, Hartree-Fock, density functional theory, many-body perturbation theory, and then we do copper cluster theory, which is a method which strikes a very good compromise between the accuracy you want to achieve and the number of evaluations of contributions to many-body perturbation theory which need to be implemented. So copper cluster theory, what does that mean? So I'm going to bring back many-body full configuration interaction theory. And let me just quickly remind you of that. We just put it up in the previous lecture. So FCI for us stands as the benchmark. If you can diagonalize, you have everything. And in in the second midterm, you're actually going to compare perturbation theory with the exact diagonalization. So in that case, if we are now just targeting the ground state of a system, and we label this as a psi 0, this is the exact one, we would write it out as 1, because we use this intermediate normalization. We have the correlation operator multiplied with phi 0. And the phi 0 is the non-interacting ansatz for the ground state. And this is now given by this series where we get the coefficients by diagonalizing. So we would then have a B, I, J. We have the new coefficient Cij, AB, and then we have phi ij. Let me just correct it a little bit here. Ij, AB, and this continues all the way to the final n particle, n hole excitations. When we did the many-body perturbation theory, what we had then is a wave operator. So if we look at many-body perturbation theory and Rayleigh-Schrödinger perturbation theory, which is the one which is normally implemented, because you can calculate order by order all terms, the price you pay is these unlinked diagrams. So in that specific case, we have a C, which is now acting on, so if we just look at how it acts on a state here, actually, I forgot to write one thing here, sorry for that. So let me just, this is C acting on phi 0, sorry, I forgot that one. So if you look at this one, if we take the expression we had in perturbation theory, and we are looking at the correlation operator, or it's often also called the wave operator, this goes to infinity, and then we have this operator R, which we defined before the break, multiplied with the Hamiltonian to the power of K, and this acts on phi 0. And it's common then to just put an L here to indicate that you only keep linked diagrams. And this term is the one which we have defined earlier as a sum over M. We have the outer product, phi M. I'm just repeating things which we put up earlier, minus epsilon M. So that's the wave operator which we get to a given order. Now, what we are going to do is actually to rewrite this equation which you see here But instead of setting up the C's, we're just going to relabel it. So in many-body perturbation theory, what we have then is that these C's are actually defined by these terms here. So if we do the wave operator to first order, as we saw before the break, then we had an expression for the CIA, and we had also an expression for CIJAB. And then you get higher order contributions. So when you diagonalize in the second midterm, you will obviously get these terms here by diagonalization. And then we are going to calculate by hand, but we will stop at the wave operator to first order. Because if you go to second order or third order to wave operator, there will be many, many more contributions. And you will not be happy. That's another thing, because it's not very exciting to add more and more contributions. So second order reveals already some of the basic patterns. So what we are going to do now is simply to bring back something which we call Fowler's theorem, which we discussed a little bit early in the semester. And we're also going to make a simple ansatz. And we're just going to say now that the wave function is just given by one particle, one hole excitations. So let's just make that as an ansatz, okay? So that means that we are going now simply to make an assumption. And the assumption is that this operator C acting on phi 0 is just given by, so this is what we would get if we were to diagonalize a Hamiltonian set up only by the ground state and one particle, one hole excitations. Now, in order to distinguish this from full CI, so when you see the C's here, then I'm thinking of full configuration interaction theory. But now I'm going to replace these ones with a new term. And this is the TIA. In principle, these are the unknown terms. This is actually where we have all the complications. And I'm just going to call this the amplitudes. And they represent one particle, one hole excitations. So these amplitudes, what I can do now, if I bring back Fowler's theorem, and you remember that I can express a general Slater determinant. So let's say psi 0. That could be expressed as the exponential, and then I have a sum over AI. If I now bring in the exact diagonalization coefficients, that could be one way of writing it. But now I'm just going to stick to these amplitudes. And because I'm going to treat them as unknown parameters, which I'm going to extract from my algorithm for copper cluster theory, or I could use many-body perturbation theory, or if I diagonalize, then I have them from diagonalization. So then I have AI, and this is acting on the ground state, like that. So this was a general Slater determinant when we only had one particle, one hole excitations. And we actually proved that this expression is correct. So it means that a general Slater determinant, if you just have the 0 particle, 0 hole, and 1 particle, 1 hole excitations, you can actually write out the exact Slater determinant as a linear combination of all 1 particle, 1 hole excitation. So if you look at this one now, it can be tempting to say that now I define an operator for excitations. So I define an operator which I call for T1. And my operator is just the sum over the particle hole states, single particle states. And then I have my A dagger, AI. That means that I can rewrite this state, psi 0, in terms of an exponential over this T1 acting on phi 0. So this is just a rewrite of what we had. If I then just use the standard Taylor expansion, this is nothing but 1 plus T1 I should put hats here, T1 plus T1 squared divided by 2 factorial plus 1 over 3 factorial, T1 cubed, etc., acting on phi 0. So what I have here is nothing but a rewrite of the whole general Slater determinant in terms of 0 particle, 0 hole, and 1 particle, 1 hole excitations. So this expression here is something which we actually proved, and this is an exact way to rewrite the wave function if we only have these types of correlations. Okay? So this is called the exponential ansatz. And in our case, if we only have 1 particle, 1 hole excitations, this gets a naming in copper cluster theory, and it's just called singles excitations. This is often called just singles. Now, we still haven't done anything. We haven't found any expression for the t's. So the unknown coefficients are obviously the t's here because we are able to define an ansatz for the ground state. And then we need a recipe to find the t's. So if you diagonalize, you have them immediately. If you do perturbation theory, you would find them order by order. So do we have a way by which we can do perturbation theory or perturbation theory inspired approaches where we can sum these coefficients to infinite order? That means, is there a way by which we can actually obtain what you see here? If I do many-body perturbation theory, I will get terms order by order in these coefficients. So the generalized ansatz now is actually so the general ansatz, and you can actually show that this gives a similar exponential ansatz, is that we define a general T operator, which is now given by T1 plus T2. So this is actually 2 particle, 2 hole excitations, plus T3, which is 3 particle, 3 hole. And this continues all the way up to T, N particle, and N hole excitations. So in principle, what you're doing here is nothing but writing down all the possible excitations, which we also had from the standard CI theory, because if you think of that one, if you look back at CI theory, that will simply contain all these terms. So what I'm setting up here is nothing but the general wave function as a linear combination of all Slater determinants you can make. So here there is no approximation. The approximation comes in when you truncate here. And that gives you different types of approximations to your copper cluster theory. So it means that you can then write out the exponential ansatz. And this is what we will pick up tomorrow when we start discussing copper cluster theory. But we will also spend time during the lecture tomorrow to discuss the midterm. So we will have a lecture first, and then we will discuss the midterm afterwards, and then we will have the next 2 hours to just discuss and work on the midterm. We hope that's okay with everybody. And what we have then, if we use this exponential ansatz, so with Fowler's theorem, we could prove this exactly. You can also prove it for the other ones. It's a little bit more complicated, but it can be proven. So it means that psi 0 here is then given by E of t, so this operator, and then acting on phi 0. And that means that when you spell it out as a Taylor series, this is going to be given by 1 plus T1 plus T2 plus T3. And then you have all the other terms of the T, N particle, N hole, if you don't make any truncations. And then you get the high order terms. You get plus 1/2 T1 squared. You get plus T1, T2 here. You get plus 1/2 T2 squared. So this becomes quite messy at the end. and then multiplied with phi 0. There's an important thing here, and it's easy to see that these different operators, they commute. Let's give by 0. And now they are the approximations which are being made in the literature, the most popular ones. And some of these give actually pretty good results. And this is where we will start tomorrow. So the approximations, there are some famous one. So T is equal to T1. This is actually called CC, copper cluster singles. S for single excitations. We have 2, we have T, and this is the one which we will discuss in connection with a midterm. So we are not going to let you guys write a copper cluster code for the midterm. I will give you that one next week so you can see how you can implement it. And this is something you could use for the oral examination if you want to. But in a midterm, we are just going to look at the many-body perturbation theory, FCI, and Hartree-Fock. So T2 is normally called copper cluster with doubles. So this is a 2-particle 2-hole. The one which is widely used is simply to assume that T is equal to T1 plus T2. This is called CCSD, singles and doubles excitations. So we include 1-particle 1-hole and 2-particle 2-hole excitations. And finally, there's a one which is called T1 plus T2 plus T3. And this has the acronym CCSDT, singles and doubles and triples. This leads to many more terms. So with singles and doubles, you have something like 30, 40 terms to evaluate. If you do triples, you get closer to 1,000. And this just explodes. So if you take all the excitations, then you have the exact wave function. So keep in mind that what we want now is an approximation. But it is an approximation which, due to the exponential ansatz, sums these terms to infinite order. So it has more than perturbation theory. So I'm going to stop a little bit earlier today, simply because as I said, we are going to have a PhD exam here.